name is Megan Mancuso, and welcome to Great Eats, the Polymer edition. Have you ever wondered what makes Jell-O Jell-O? What is this alien thing with the wonderful elastic ability to jiggle back to its original form after experiencing shear stress? This gel is actually made up of edible polymers linked together, trapping the liquid inside. A common technique used in molecular gastronomy involves reversible jellification of liquids. This is what Jell-O is. See right here? But there are many more additives that can be used to make gels with similar properties. There is one polysaccharide that has several different properties than Jell-O. Agar-agar produces a polymer gel that has a melting temperature around 90 degrees Celsius, requires a much lower concentration of gelling agent than Jell-O, and is stiffer. Agar-agar is a substance derived from algae. It is a polysaccharide composed of mostly agarose chains and agropectin. Here's an example of the agarose polymer. The agarose itself is made up of D-galactose and 3,6-anhydro-L-galactose. In order to form a homogeneous gel from agar-agar, it must be thoroughly mixed in a liquid, forming a hydrocolloid. The agar-agar chains then disperse in the liquid, which allow for it to become hydrated with the water when the solution is heated. The once stiff chains are now allowed to freely move. In order to induce the jellification process, the solution must be cooled to below the melting temperature. During the cooling process, the agar-agar chains twist together to form double helixes. The helixes then join together to form a lattice, as you can see right here. The liquids between the agar-agar helixes are then trapped, forming a gel. Unlike other gelling agents, agar-agar does not need another substance in order to initiate the jellification process. The agar-agar hydrogen bond to each other. Another use of polymers in molecular gastronomy is in the process of spherification. One of the polymer additives used in this process is a thermostable alginate. Alginic acid, a seaweed derivative, was first discovered in 1881 by Scottish scientist E.C.C. Stanford. There are two saccharides that compose alginic acid, beta-D mannaronic acid and alpha-L gluuronic acid. Here are examples of beta-D mannaronic acid and alpha-L gluuronic acid. The copolymer is formed as blocks of the saccharides bind in the C1 and C4 positions. The form of alginate commonly used in molecular gastronomy is the sodium salt of alginic acid, sodium alginate, with the hydrogen on the carboxylic acid having been replaced with the sodium ion. Right here, that would be replaced with the sodium. And in order to form a gel with the sodium alginate, a divalent cation must be added. This lets the alginate chains cross-link amongst each other as seen in this picture here. There are two common methods for spherification. The method that will not be used in today's experiment is basic spherification. This process involves adding sodium alginate to the liquid that is going to undergo spherification. A water bath is made that contains calcium lactate, the source of the divalent cations. Spoonfuls of the alginate solution are dropped into the calcium solution. The calcium ions penetrate the alginate solution and begin to jellify the sphere from the outside. Unlike the agar-agar gels, the spheres only have an outside gel layer while the inside is still liquid. Unfortunately, the jellification process will continue when removed from the calcium bath. Thus, it must be consumed quickly in order to gain the gel-liquid layer effect. The method that will be used in this experiment is called reverse spherification. As the name suggests, the alginate will be in the water bath while the calcium lactate will be in the liquid, undergoing spherification. In this method, an alginate polymer is formed on the outside of the sphere due to the calcium ions from the sphere moving into the alginate solution. And unlike basic spherification, the inside of the sphere will remain liquid. Now I will demonstrate the process of agar-agar jellification. So for this, I will take 175 milliliters of water, place it in a pot, and 2 grams of agar-agar. So now turn on the stove and put it around medium heat till the agar-agar dissolves fully in the solution. Now that the agar-agar has dissolved, I'm going to add 2 ounces of semi-sweet chocolate. Now that the chocolate has all dissolved, I'm transferring it to a beaker, letting it cool for a second. Now I'm going to make chocolate spaghetti. So I have my syringe, and I am filling it up with the chocolate solution. So now I have my silicone, whatever you call it, I don't know. Tube, maybe? Tube. So I'll fill it up. Oh, water. Almost to the end. Okay, there we go. Now, ooh, that's hot. Now I'll place it in an ice bath for a few minutes and let it gel. Now that it has been several minutes, hopefully these chocolate spaghetti will have solidified. Oh yeah, spaghetti. Whoa! Did you get that? Ta-da! Now the agar-agar, after it cooled, trapped the liquid inside, forming a gel, as you can see right here. Next, I am going to demonstrate the process of reverse spherification. Here in this bath is sodium alginate. Now this is what's going to form the polymer. And here I have some brewed coffee and calcium lactate, which is going to form or provide the divalent ions. So in order to form a sphere, I'm using an eyedropper. So I'm going to stick it inside the alginate solution in the sphere, or something that looks like a sphere form. Let's try that one more time. Guess they're not going to be spheres today. Whoops. Well, as you can see, we have a polymer forming. Let's try one more time and see if we can actually get a sphere out of this. It's hard due to the this not being thicker than the alginate solution. There we go. That's more of a sphere. See that? Let's make a few more. And this one, die, bubble. Never mind. So here we have coffee solution with some cream added. There we go. Make a few more. Alright, so now we have our chocolate spaghetti in our coffee spheres. Now we have deconstructed mud pie. A little caramel sauce. And several cacao nibs. Ta-da! In conclusion, polymers are an important part of molecular gastronomy due to their ability to alter the appearance and construction of food. Their use is ever increasing as molecular gastronomy branches out into the culinary world. Thank you for joining me on this journey into the world of edible polymers. See you next time on Great Eats. Bye.